Hello, this is Stuart Mason, Math 156, E156. We're doing a script 8a, talking about maximum likelihood estimators. I'm going to start out by examining an example from the textbook. So the Cauchy distribution with a single parameter, which we're calling theta. It's the central parameter. It's basically the median of the distribution. Okay, so suppose that we have some Cauchy distribution and we don't know the value of theta, but we have 5 samples, 1, 2, 2, 3, and 4. We can ask for any given value of theta, what is the likelihood of observing this data? If they're independent events, then the likelihood is just the product of the individual, right? So the probability of any given event is the PDF evaluated for that data point. We multiply them all together, and as a function of theta, this will return the probability of seeing the data. So now we can plot a curve, and basically as we allow theta to vary, as we guess different values of this parameter, we can see this curve that shows us how likely our data is at each of these values. And then our best possible guess for theta is going to be the value that maximizes the probability of observing our data. And so we can see by looking that it's basically in the neighborhood of 2 and 2.5, and R will gladly tell us exactly what it is using its optimize function. And this function is a shade more complicated than functions we've seen in the past. If you pull up in its help file, you'll see all kinds of documentation about its features and how to use it. But Paul started us with a very simple example, so we just give it the function we seek to optimize, our best guess for the neighborhood of the local max, which we can find, for example, by inspection in the one-dimensional case, simply by looking at this graph, and then this Boolean value maximum, which means, yes, we would like you to find the max on the neighborhood, not the minimum. We run that and we get a value both of the location of the maximum and what the function evaluates to. So this is pretty meaningless. This is sort of the probability of observing the data, but as your data sets grow larger and larger, the probability of any individual sample actually goes to 0. So just because this looks like a small probability doesn't really mean anything. It's the maximum we can do. And this is the value of theta that maximizes it. And so then Paul basically runs a similar example with a discrete distribution. I'm not really sure what is illuminating about this, because yeah, it's a discrete distribution, but the lambda parameter itself can take on any continuous values. So really this example winds up being the same. And sure enough, we get the same value as the textbook. So I just gave a speech about why this thing is always very small. In this case, it came out quite large. The reason for that is because Paul has omitted the denominator of this density function, which is just a constant, and it doesn't depend on lambda, so it won't affect the calculation, but it does affect the objective values. So that's why it came out so large. Basically, he took a shortcut. Okay, so now suppose we have some uniform distribution. We know the lower bound is 0. We don't know what the upper bound is. We've observed 4 samples between 1.2 and 5. And Paul says, well, if beta is less than 5, then we would have 0 probability of seeing this sample because we found one that's supposedly outside the range. So we know that beta has to be greater than 5. But otherwise, the density function is just going to be 1 over beta. So these are sort of, basically we just have 4 samples, right? 1 over beta to the 4th is the probability of observing this. And you can kind of tell by inspection that this is just going to get smaller and smaller as beta gets bigger, which means that the very first value that admits non-zero probability for the sample is what the MLE is going to pick. And so you can see by inspection that's going to be 5, but we'll let our optimize do its thing, and it will tell us, yep, maximum at 5, a little bit of numeric instability. And so basically, the maximum likelihood estimator for a uniform distribution with a sort of 0 endpoint and beta is just going to be the max sample. But Paul says, well, there's going to be a problem here, and I agree, right? You can kind of intuit this out. Basically, you're pretty much have a 0% chance for a continuously uniform distribution of ever actually pulling the maximum value. So your sample max will never quite be your population max, and your estimator will always be too small. And so Paul's going to simulate pulling the max 1,000 times and draw a histogram. And sure enough, it punches right up against 5, but I bet none of these values are ever actually 5, which beta.hats double equal 5, none. And if we look at the mean of the beta hats, we actually get a value that is centered around 4. So basically the average estimator is 4. And Paul says, well, we can unbias this by multiplying it by a factor of 5/4. So you can do the algebra and basically show that this has a similar problem as the standard deviation estimator, and you need to unbias it by creating a coefficient of the sample size. And so I think in this case we had 4 samples, so it's n plus 1 over n is the unbiasing constant, and fortunately that goes to 1 as n gets very large, which is good. Okay, so in topic 2 we're going to use maximum likelihood to estimate distributions with more than one parameter. The idea is exactly the same principle. It's a little bit harder to visualize the situation without drawing plots in 3 dimensions, which R can do, but we're not going to do in this script. Paul says let's load the stats4 library to get access to some new functions. And we're also going to use the log likelihood instead of the likelihood. So I'll talk about that in just a moment. First, let's load in our observation. So 1, 2, 2, 3, and 4. This is from the Cauchy example that we started with. Great. So maximizing a function is the same thing as maximizing the log of that function. And when you take the log of a product, you're left with a sum of logs, which we find that sums are often easier to work with than products when you're maximizing. If you just think about one-dimensional optimization, you're going to be taking derivatives. The derivative of a sum is pretty easy to compute. The derivative of a product is a little bit more tricky to compute. And so that's sort of one reason why you might believe me that taking the logarithm makes your life easier. So we're going to find a function that just sums up the Cauchy density, and we're saying, yes, give us a log. So Paul says, for some reason, this function has to be vectorized. I haven't tested this. My hunch is because it has a vector argument. So when you're plotting things with vector arguments or doing like vectorized operations on functions with vector arguments, R will do you a favor and return a list, but you need to vectorize to override that behavior so you can plot the curve. So now we're going to basically optimize this, but instead of using the optimized function, we're going to use this MLE function. And it looks like we seed it with an initial guess. And it returns the coefficients, 2.2116. So here's just the Poisson example again, and exact same idea. So let's go to the interesting piece, which is what you do when you have more than one parameter. So suppose we have a normal distribution, and we want to know what mu and sigma are. So here's our data. And our sample mean is 3, and our sample standard deviation is 1.58. This is now a function of 2 variables, right? Because we can allow both of our parameters to vary, but it's still going to be this negative log likelihood of the probability of observing the data as a function of the different possible values of mu and sigma. So Paul points out that we really can't plot this very easily. We can plot it, and we can explore its plot, but instead, Paul skips right to this part where he uses the MLE function, and he's going to seed mu to be near 2 and sigma to be near 3. Not really sure where he got these guesses, although it wouldn't be super exciting to go with the MLE estimators already. For mu, we get the sample average, which we expected. For sigma, we get the 1 over n standard deviation, not the 1 over n minus 1 standard deviation. Because this is the MLE estimator. So much like the beta estimate in the uniform distribution, the MLE estimator in this case has a bias. And so Paul points out that if we just compute the average deviations from the mean and take the square root. This is basically like the population standard deviation. That's what we get here. And so again, now here we're talking about unbiasing, right? So you can multiply by, in this case, n over n minus 1. Okay, so now we're going to use some real-world data and talk about the two-parameter Weibull distribution. So we're going to use the turbine data set, and we're reading in wind speeds. So we have 168 data points, and the average is 6.85. So the Weibull distribution, I think, is a special case of the gamma distribution, but we'll have to look into that. In any case, this is basically exactly the same code, except we've changed dnorm with dWeibull. So seeing the data for different values of the parameters k and lambda. And we say, yeah, see lambda near 6 and k near 2, and it spits back these estimates. And so now let's take a look at the sort of resultant Weibull distribution and if it agrees with our data. So we can draw the histogram and plot the overlaid curve. We've really recently only done this with simulated data, so it's pretty rewarding to see it in action with a real data set, and it works. For once, we actually get data that look like they line up with the theoretical distribution. And so now Paul's running through some code from the textbook to compare the distribution functions. So here's the curve is the theoretical cumulative distribution for Weibull with these parameters, and then we have the piecewise actual empirical ECDF. Finally, we got the Weibull quantiles with QWeibull. We say for all the values 0.1 to 0.9, going up by 0.1 with these parameters. So these are the deciles that cover the 10% of the data, right? Here's the median, etc. And so then Paul asks, okay, what's the range? And then he basically augments his vector such that it encompasses the entire range. So he picks a value less than the negative, he picks a value less than the minimum, and a value greater than the maximum, and bookends his Q vector that way. And then we're going to draw a histogram with the breaks defined to be the Q vector we made. So in the middle, we have these kind of nice evenly spaced breaks that we defined before. On the edges, we have these very kind of strange fatter breaks, which Paul manually added. And then the histogram actually has a counts attribute, so we can use this to store the count in each of the breaks. These are just in order. And because of the way he picked it, we expect to see 10% of the data in each decile. And now we're just doing a goodness of fit test with the chi-square statistic. So now we're asking what's the probability of seeing this chi-square statistic? Well, pretty high. And so basically, this is sort of statistically justifying the picture we drew here and here that show how well the data seem to line up visually with the Weibull distribution, and it would be reasonable to model wind speed as a Weibull. All right, great. Hope this was helpful, and I'll see you guys back here for script 8b.